Okay, formulation for freeze-dried drug molecules. So buffering agent, again, for pH adjustment, regular buffering agent can be used. Sodium or potassium phosphate, sodium acetate, sodium citrate. We already talked about this before. But unique thing is here, lyoprotectants are added. Again, remember lyoprotectants, those are the molecules that can protect your API during the drying process. Okay, so what can be used? Sucrose, trehalose, dextran, and amino acids such as glycine. So glycine is the simplest, smallest amino acid. Okay, these non-harmful sugar or amino acid can be added to protect your drug molecule during the drying process. Okay, so lyoprotectants are unique in a freeze-drying drug formulation. And then surface active agent, we already talked about this. Competitive binding agent, tonicity adjuster, antimicrobial agents. Those are commonly used. There's nothing unique about those. Okay, and then freeze-dried formulation containing small molecules. They do not require any additive excipients because of their large quantity, or additives required for relatively simple purposes. Okay, so what it means is, if it's chemical-based drugs, those are small molecule drugs, and they don't need any additive excipients because they exist in large quantity, like higher than 100 milligram per container concentration. So there's no special additive required. However, if you're dealing with the biological molecule, which are considered as a large molecule drug, right? So during freeze drying, it requires more formulation challenges because biological molecules are very susceptible for changes. So you have to make sure that they are being protected. Okay, so under those conditions, you need to add one more additives like bulking agents, lyoprotectants, surfactants, or buffers. Okay, the reason is biological molecules are much more susceptible for degradation during harsh freezing drying condition. Okay, not only that, some of those large molecules exist at very low concentration. Okay, between very low milligram concentration to nanogram per mil concentration. So under those conditions, you don't want to lose them during your freeze drying. So make sure that you may need to add competitive binders like human serum albumin, extra proteins that can protect your drug molecule from sticking and then to the container, and you lose those. Okay, so you have to add extra protection. That's what it means. So it will prevent absorption loss. Okay, so filters, tubings, or primary containers. That's what it means. Okay, and then you may need to add something like mannitol. We talked about it, and sucrose as tonicity adjuster modifiers. Okay, so instead of adding sodium chloride, you can add mannitol and sucrose. Okay, to adjust the concentration of the salt. Salts are avoided because they decrease the critical temperature of the formulation. So salts, normally for tonicity adjusters, sodium chloride can be used in many other formulations, but for freeze drying, you don't want to do that. Sodium chloride will especially change the eutectic glass transition temperature. We'll talk about freeze drying principle, the physics of that, in a separate lecture. But there are important temperature points where your drug molecule will be frozen nicely. We call that eutectic temperature. Or it may be frozen, but you will lose the structure of your drug. Then we call that maybe glassy transition temperature, amorphous temperature. You don't want those. So, if you add salt, you tend to mess up those temperatures. So that's why you want to move away from salt when you formulate your drug. Okay, that's what it means. Excipients that stabilize the protein against the problems of denaturation and agitation caused by drying. So we call the lyoprotectants, right? We call that during freezing process, we call it cryoprotectants. Understand the difference between lyoprotectants and cryoprotectants. Lyoprotectants protects against drying condition, and cryoprotectants, it protects against the freezing condition. So that's a difference, right? So sugars of different kinds, sucrose, lactose, glucose, trehalose, and the polyols like glycerol, mannitol, sorbitols made out of polysaccharides, and amino acids, simple amino acids like glycine, alanine, lysines can be used, and as well as polymers like polyethylene glycol, dextran, polyvinyl pyrrolidont. Those things are used as cryoprotectants. Okay. The most preferred cryoprotectants are PEG, polyethylene glycol, or sucrose or trihalose, sugar-based molecules. And proteins may exist or experience adverse effect when the sublimation happens. Okay, sublimation again, what? Crystallized and then evaporated, vaporized. Okay. So when stored in the dry state, so such proteins need stabilizers to protect proteins from, freeze-dried. You may want to call lyoprotectants, add lyoprotectants. Okay, they normally work as a water substitute when the water is removed. Okay, through drying process, the place where water crystal was is substituted with these molecules. They're lyoprotectants. That's what they do. So sugar molecules are excellent lyoprotectants. Okay, because they can form hydrogen bonds similar way and the water molecule does with the protein. Okay, so lyoprotectants, understand what they do. Okay, so sometimes, okay, the same excipient can be used for cryoprotectants and lyoprotectants. Okay, sugar, trehalose, sorbitol, we talked about sugar over and over. Yes, they are both cryo and lyoprotectants. That's what it means. Okay. Concentration of stabilizers. If cryoprotection is needed, the relevant concentration of stabilizers in solution, it's about 0.3 mole or above. Okay, so it's a lot of stabilizers. Okay. If lyoprotectant is needed, the mass ratio between the sugar and protein will be 1:1. Again, it's a lot, okay, needed for a proper stabilization. So gelatin, albumin are also used to provide stabilization during the lyophilization process, it says. So once your drug is freeze-dried, how much moisture should be still remaining in there? How much dryness is there after it's freeze-dried? So the residual moisture, that's how we call it. That's the moisture still remaining after freeze-drying has taken place. So it's about 0.5 to 3% of the total volume. You can still have some moisture in there. So that's what it means. It's not 100% dried. And then where water resides in the freeze-drying matrix and what solid morphology exists are very important. So we'll talk about that again in the freezing drying lecture. Okay, the matrix is crystalline, water exists as surface water and is not likely problematic. However, if the matrix is amorphous, so understand eutectic, crystalline, amorphous. Amorphous means, when your drug is freeze-dried, it loses structure, so it just collapses. So there's no visible structure after freeze-drying. That's what amorphous is. So a solid which is not crystalline, okay, as its atom arranged in random order, is called glass state or amorphous state. So you don't want that when you freeze-dry it. Okay, the excess water may interact molecularly with the drug and cause unacceptable degradation. So you want to avoid this one as well. So how do you remove your water during the freeze drying is very important. Okay, so we'll talk about that in the freezing drying lecture. So let's talk about mannitol. So mannitol looks like this. It has this chemical structure, and mannitol is one of the major excipients used in the lyophilized freeze drying formulation, because mannitol helps to stabilize your drug molecule during the freeze drying process. So mannitol can crystallize during freeze drying, okay, if you add mannitol in your formulation, okay. So you can, by doing so, you can protect your drug molecule. Okay, just like sugar molecule, like sucrose, trihalosane, citric acid, phosphate, buffer, polymers, and things like that. So mannitol crystallizes into different polymorphic forms as a function of concentration and freeze drying rate. So what it means is it's not going to present you kind of uniform crystal structure. So it depends on under what temperature condition, under what speed, the vacuum condition, it may form different crystalline. It's what it means. So although it's a great cryo and lyoprotectant, you need to figure out the best concentration of mannitol when you use it in your freeze drying formulation. And that's what it means. Normally, when you select your mannitol, when you test it, you may have to anneal. So what that means is, when you freeze and dry it, before you dry it, annealing means after primary freezing, you can thaw it out by heating up again, and then you freeze it again. So that's what annealing is. Freezing, thawing, a few times you can repeat it, okay, to get a good crystalline structure in your drug molecule. So annealing may be needed, okay. The mannitol can, when it is crystallized through annealing process, it will give you a better stable structure, so the vaporization of water may happen more easily. Okay, after water vaporization, your drug molecule can still have very good eutectic structure. So that's what this means. Okay, so mannitol is certainly a good excipient in freeze drying formulation. Okay, and then plasticizers such as glycerol, ethylene glycol, and DMSO, they can be used in the formulation. Okay, so they can fill small volume left open by the larger host glass former, restricting motion and slowing the fast dynamic of glass and subsequent protein degradation. So the plasticizers kind of protect your drug molecules during freeze drying. That's what it means. Okay. And steps in the development of freeze drying formulation process. So how do you know what is the best formulation for your freeze drying drugs? That's what it means. How do you determine what excipient should be the best? Okay, so these are the steps in your formulation selection. Number one, determine the critical temperature of the drug alone using thermal analytical methods like DSC, differential scanning calorimeter, and the freeze drying microscopy. Those are two main tools that you can use to determine the critical temperature, the primary freezing temperature or secondary freezing temperature, annealing temperature, all those things. Okay, so when you do that, you use these two instruments when you select, because they will allow you under what maybe freezing point your drug will crystallize, okay, TSC, and then under what speed your drug molecule would not collapse. So we'll talk about this again in the next chapter. And then freeze drying the drug alone and determine what happens. So without adding many excipients, what it means, you try to freeze dry your drug itself that's maybe mixed up with the main solvent, and see what happens to your drug. Characterize your drug molecule first, and then if excipients are needed, start with commonly used ones. Well, commonly used, well-known ones. That's what it means. Okay, so the acceptable ones like a sugar molecule or maybe mannitol, those should be tried first. And then conduct initial screen test, freeze thawing cycle, or agitation studies to screen initial formulation to eliminate worse ones. Okay, you can try different formulation by adding different excipients, but conduct various tests on the different freezing cycle and see which one works the best. Formulation should have solid content between 5 to 30% with a target of 10 to 15%. So you should not have any collapse of your drug. You should still have the solid content about that much. Okay, and determine the maximum allowable temperature permitted during the freezing and primary drying of